Every morning, millions of people perform the exact same routine. You stand at the bathroom sink, wipe the fog off the glass, and stare at your own face to apply shaving cream or brush your teeth. But there is a strange physical contradiction happening right in front of you. When you raise your right hand to your cheek, the person in the glass raises their left hand. The mirror seems to have flipped your entire world horizontally, which raises a specific question. If the mirror can flip an image from left to right, why doesn't it flip you vertically? Why isn't your reflection hanging upside down? To understand what the glass is actually doing, we must look at the behavior of light. Light is energy that, when traveling through an empty space or a uniform medium like air, always moves in a perfectly straight line. When this straight traveling light collides with an opaque, smooth, and shiny surface, like the silver backing of your bathroom mirror, it cannot pass through. Because the surface is perfectly flat, the light doesn't scatter, it bounces. This physical interaction is the basis of every reflection. The image in the glass is governed by strict, highly predictable geometric rules. To see those rules in action, we need to zoom down to the microscopic surface of the mirror, right where the light makes contact. This diagram shows a cross-section of a flat plane mirror. The incoming beam of light striking the surface is the incident ray. The beam of light that bounces away from the mirror after the collision is the reflected ray. To measure exactly how these rays behave, physicists draw a dotted line straight up from the surface. This is the normal line, a perpendicular reference line used to accurately measure the angles of the light coming in and the light going out. This reveals the universal law of reflection. The angle of incidence is always exactly equal to the angle of reflection. If the incident ray arrives at a steeper angle, the reflected ray perfectly matches that new angle as it leaves. A mirror does not capture or create a picture of your face. It simply redirects millions of individual light rays with mathematical precision. But redirecting light is only half the equation. To get an image, those bouncing rays have to travel from the mirror and enter a human eye. Look at this top-down view of a person at a mirror. Our brains have a built-in biological assumption. They always assume light travels in a continuous straight line. Your brain is unaware that the light just bounced off a surface, so it traces those rays backward. Because the brain follows those lines straight through the glass, it constructs an image that appears to exist physically behind the mirror. Because the angles of reflection are symmetrical, the geometry dictates a strict distance rule. The image appears exactly as far behind the mirror as the real person is standing in front of it. If you were to walk behind your bathroom wall and place a physical projector screen exactly where your reflection appears to be, the screen would catch absolutely nothing. This is a virtual image. It cannot be projected onto a screen because the light rays do not actually exist behind the mirror. They only appear to originate from there. The mirror isn't swapping your left and right sides. It is reflecting you front to back. Light hitting the right side of your face bounces straight back, remaining on the right side of the virtual reflection. It is a direct geometric reversal, not a horizontal swap. This front-to-back reflection is why you don't flip upside down. The light from the top of your head bounces straight back to the top of the image. The reflection remains upright, a property physicists call an erect image. The resulting image is virtual, upright, and identical in size, an illusion constructed by our brain's own assumption about how light moves through the world. Because we understand exactly how plane mirrors flip images front to back, a process known as lateral inversion, we can use this geometry to our advantage. Take an emergency vehicle. The word ambulance is deliberately printed in reverse across the front hood. When a driver checks their rearview mirror, the mirror's natural front-to-back reflection flips that text again. The driver reads it correctly and yields the right of way. We can also use multiple plane mirrors to deliberately bounce light around obstacles, like a sailor using a submarine periscope. By placing two flat mirrors inside a tube at 45-degree angles, the light utilizes the law of reflection twice. It enters the top, bounces down the tube, hits the second mirror, and bounces directly into the viewer's eye. Nature follows these exact geometric rules. When a body of water is smooth, it acts as a massive plane mirror, providing a uniform reflection that creates a virtual replica of the landscape above. Virtual, erect, same-sized, and laterally inverted. These are the constants of a plane mirror image. Next time you look at your reflection in a dark window or the back of a spoon, try to trace the path the light took to get there.